Assalamualaikum, my name is Muhammad Adam Azim bin Azman, and today me and my team will present to you guys about nuclear reaction in star. Okay, so nuclear reaction in star are the process that power star. So nuclear reaction is like a power grid to the star and generating the energy that allow them to shine and sustain their structure. This reaction occurs in the core of the star where temperature and pressure are incredibly high. There are several types of nuclear reaction that occur in star, primarily involving the fusion of lighter atomic nuclei into heavier nuclei. Here are the main types. So first we have proton-proton chain reaction. Second, CNO cycle, which is carbon, nitrogen and oxygen. The third one is triple alpha process, and the fourth, advanced nuclear burning. Okay, so now we have the importance and significance of nuclear reaction in star. Like I said before, the nuclear reaction in star is what gives the star itself the source of energy. So this energy generates the lights and heats that star emits, making them visible across the universe. And also, the sun energy is essential for life on Earth. It drives climates and weather, enable photosynthesis in plants, and support ecosystem. So second one, we have element formation. So for production of element, nuclear fusion in star produce heavier elements from lighter ones. Example is hydrogen fusing into helium. This process, known as nucleosynthesis, continues in successive stage, forming elements up to iron in the most massive star. After that, we have stellar evolution. The energy produced by nuclear reaction creates outward pressure that counterbalances the inward pull of gravity. So, as we know, Sun is very big and have a really great power of its own gravity. So, the energy produced by nuclear reaction counterbalances the pulling of the gravity. This equilibrium maintains the star structure and prevents it from collapsing. For cosmic balance, enrichment of the interstellar medium, the elements produced in stars are released into the interstellar medium through stellar wind and supernova explosion. This material becomes the building block for new stars, planets, and ultimately life. So after the star collapse through supernova, for example, it will give another chance for new star to forming or maybe another planet.
The methodology of nuclear reactions in stars involves several key processes. The first one is nuclear fusion. Stars primarily generate energy through nuclear fusion, where lighter atomic nuclei fuse together to form heavier nuclei, releasing energy in the process. This is the primary source of a star's luminosity. Thermonuclear reactions. These reactions occur at extremely high temperatures and pressures found in the core of stars. The most common fusion reaction in stars like the Sun is the proton-proton chain, where hydrogen nuclei fuse to form helium nuclei. The third one is energy generation. The energy generated by nuclear reactions support the star against gravitational collapse, which is hydrostatic equilibrium, and provides the energy that is radiated away as light and other forms of electromagnetic radiation. Four is nuclear reaction rates. These rates depend strongly on temperature and density. For example, higher temperatures increase the rate of nuclear reactions due to increased particles velocity, overcoming the Coulomb barrier, repulsive force between positively charged nuclei. Stellar evolution and nucleosynthesis. As stars evolve, they undergo different nuclear reactions depending on their mass and composition. Heavier elements beyond helium are formed through various nuclear processes in stars during their lifetime, which is stellar nucleosynthesis, including during supernova explosions for the heaviest elements. Neutrino emission. Nuclear reactions in stars also produce neutrinos, which are very weakly interacting particles that carry away a significant portion of the energy generated in these reactions. Neutrinos play a crucial role in stellar dynamics and are studied through neutrino astronomy.
Next, nuclear reactions in stars are fundamental processes driving stellar evolution and energy production. However, these reactions face observational validation. So here are some of the key challenges encountered for the nuclear reaction. Okay, first is extreme conditions, which is the nuclear reactions in stars occur under extreme temperatures and pressures, and it's particularly in the cores of stars. For instance, in the sun, the core temperature reaches about 15 million Kelvin. So these conditions are difficult to replicate and study in laboratory settings on Earth. Second is helium fusion and advanced burning stage. So these challenges is while hydrogen fusion via the proton change or CNO cycle is relatively well understood, and the diffusion of heavy elements like helium, which is the triple alpha process, and the advanced burning stage, which is carbon, neon, oxygen, and silicon burning, pose greater challenge. These processes require higher temperature and pressure. Also involve more complex nuclear networks leading to uncertainties in stellar evolution models. So next is neutrino emission, which is these challenges um, like nuclear reactions in stars, especially those involving in the CNO cycle and advanced burning stage, produce neutrinos. So the detecting and measuring these neutrinos is difficult due to their weak interactions with matter. However, neutrino observations are crucial for understanding stellar interiors and validating theoretical models. And last but not least, astrophysical observation is the one challenges encountered. So observationally, it is challenging to directly measure the outcomes of nuclear reactions in distant stars. So astronomers rely on indirect evidence such as spectra, luminosity, and neutrino flux. Discrepancies between observation and theoretical prediction highlight the need for more precise models and better observational techniques. So, those addressing this challenge require advancements in both theoretical physics and observational technology, as well as sophisticated simulation that can be better replicate the conditions inside the stars.
Nuclear fusion in star. Nuclear fusion is the process by which two light atomic nuclei combine to form a heavy nucleus, releasing a tremendous amount of energy. This process powers stars, including our sun, and is the fundamental reaction that produces energy in these celestial bodies. In star, fusion typically involves the hydrogen nuclei fusing to form helium. This process occurs in several steps, with the primary pathway being the PP chain and the CNO cycle. And as for importance, nuclear fission in star, which is energy production, scientific research, supporting life, and element formation. Examples that related to nuclear fusion in star. The sun primarily used the PP chain reaction for nuclear fusion. Hydrogen bomb used nuclear fusion of hydrogen isotope to produce a massive explosion, much more powerful than fission bomb. Stellar nucleosynthesis, more massive than the sun, and this star use the CNO cycle and in later stage can fuse heavier elements in their core. And helium flash happens in the core of red giant star once they have exhausted hydrogen in their cores, and helium fusion ignites suddenly. Rapid onset of helium fusion into carbon and oxygen. Applicability in daily life. Clean energy source. Fusion energy produces minimal greenhouse gases and does not contribute to air pollution unlike fossil fuels. electricity generation, fusion power plants could provide a consistent and reliable source of electricity, supporting the grid with baseload power. Desalination, fusion power could be used to drive desalination plants, converting seawater into fresh water, thus addressing water scarcity issues in arid regions.
Next, recent studies in modern physics have made significant strides in presenting complex concepts in more accessible and engaging ways, covering areas from quantum computing to the mysteries of the cosmos. So, first is quantum computing. In quantum computing, researchers have made advances in creating more reliable quantum computers by utilizing non-abelian anyons. So, these particles store information in their rates, which could lead to error-tolerant quantum computing. So, in new quantum error correction codes have also been developed, potentially solving some of the current challenge in maintaining quantum bit stability. So next is gravitational waves and black holes, which is the James Webb Space Telescope, which the short form is JWST, has provided unprecedented insights into the early universe. So it's revealing numerous supermassive black holes and bright galaxies that challenge current cosmological theories. So these findings are pushing scientists to reconsider how such massive structures could form so quickly after the Big Bang. Last but not least, for quantum networks which is progress in quantum communication includes the development of quantum repeaters based on the trapped ions. So this device can extend the range of quantum networks by addressing photon loss in optical fibers, potentially enabling long-distance quantum communication. So these studies not only advance for our understanding of fundamental physics, but also the highlight the ongoing efforts to make these sophisticated concepts more comprehensible and applicable in practical technology.
So next, we move to the self-development for a career. For potential career related, it has engineer, astronomer, nuclear physicist, and so on. And for the engineer, it is provide technology for space missions that investigate nuclear reactions and stars. It is used the concept of nuclear reaction in order to develop advanced technology fusion-based nuclear energy system. And the second is astronomer, which is it makes observation of stars and their nuclear activity using telescope and other instruments. It is also focused on the detection and interpretation of radio wave released by stars and other celestial bodies. And the last one is nuclear physicist. It create and improve the nuclear process models for stellar environment, and it using nuclear reactors or particle accelerators in experiments in order to understand nuclear reaction better. For the proposed and specific skills for nuclear reaction in stars, it also has three, which is technical skills, analytical skills, and research skill. For the technical skills, it is full of the understanding of nuclear reactions in stellar environment, which is strong knowledge of linear algebra, differential equations, and calculus. For analytical skill, is the ability to use a methodical approach to solving complex scientific problems. It also has strong analytical skills to interpret data and validate models. For the research skill is this ability to plan and carry out experiments, frequently with nuclear reactors or particle
The
accelerators.
significance of continuous nuclear reaction in stars. Studying nuclear reactions in stars is crucial for several reasons related to career development. First one is global collaboration. It provides opportunities to collaborate with researchers worldwide, fostering networking and exposure to diverse perspectives. Second one is career opportunities. It opens doors in academia, research institutions, and even industries requiring expertise in nuclear physics or astrophysical modeling. Fundamental research skills. It involves advanced physics and astrophysics, which hones analytical and problem-solving skills essential for a scientific career. Four is interdisciplinary knowledge. It bridges astrophysics, nuclear physics, and computational modeling, providing a broad foundation beneficial in various scientific disciplines. Cutting-edge technology often involves using state-of-the-art telescopes, detectors, and computational tools, offering hands-on experience with advanced technology. Impactful discoveries. Its potential to contribute to significant discoveries or breakthroughs in astrophysics, enhancing professional reputation and career
And
prospects.
next is the challenges and strategies for nuclear reaction in star. For the challenges is first the huge distance between stars and the opaque nature of their interior make it impossible to directly observe nuclear reaction within them. And the second one is because of theoretical limitation and few experimental data, nuclear reaction rates at stellar temperature often remain undefined. And for the strategies is the first is make use of indirect observation methods like neutrino detection and spectroscopy. Use telescope in orbit to collect high resolution data. Second one is measure reaction rates in controlled environments by conducting experiments. To measure uncertainty and improve models, we need to apply statistical technique.